Logic. When most people talk about logic, they typically mean common sense. For instance, when we put our pants on our legs instead of our arms, that's more in the realm of common sense than logic. When a mathematician or philosopher talks about logic, they typically mean something else. Mathematical logic is a system of quantifying or qualifying the world around us into simple or complex statements that can be determined to be true or false. Much of logic centers around an accepted shorthand called logical notation. Large, clunky statements such as, "The Earth is the center of the universe," or "Dick Clark is the oldest man alive," are shortened to one-letter variables, typically P or Q. The connector words and phrases we use, such as "and," or "is necessary for," or "there is at least one of," are also shortened, but into symbols. Let's start with something simple. The simplest operator is the negative, denoted with this hooky dash thing. So if we take the statement P to mean the sky is blue, then dash P, or not P, would mean the sky is not blue. Then we have the conjunction, which means and is represented by a wedge. If we take Q to mean grass is green, then P wedge Q would mean the sky is blue and grass is green. There's also disjunction, which connotes or, and is represented by a capital V. So P capital VQ would mean the sky is blue or grass is green. Note that in this instance, if both the sky is blue and grass is green, the statement is still true. This or is not exclusive. Finally, we have the conditional, denoted by an arrow. P arrow Q would mean if the sky is blue, then the grass is green. And those are the basics. You can then spend time filling in truth tables by assigning values of true or false to P, Q, or any other variables you have, and then seeing which combinations produce a true statement. Now often P or Q are not set statements. There's usually at least one piece of information to be filled in. Instead of saying P means a person has blonde hair, we instead say P of X means X has blonde hair. We can then set a domain, or possible values for X. In this instance, our domain might be all people. So using that particular P of X, we can also assign a Q of X, which might mean X has light skin. So the statement, if P of X, then Q of X, would mean if a person has blonde hair, then they have light skin. Usually we want to specify whether our statement applies to everyone in the domain, or if you're saying it applies to at least one individual in the domain. For this, we have quantifiers. First is the universal quantifier, which uses an upside-down A. But in order to use it, we have to put a variable directly after it. For instance, upside-down A x, or upside-down A y, etc. This would mean for all x, or for every y, or something like that. You're just saying that your statement applies to every individual in your domain. Now this means nothing on its own. We have to attach it to a statement. If we attach it to our old P of X, we'd get for all X, P of X, meaning everyone has blonde hair. Now you could restrict your domain to, say, Swedish people, and then it would mean all Swedish people have blonde hair. But watch how it takes a slightly different meaning when we throw in a conditional. For all of X, if P of X then Q of X would mean everyone who has blonde hair has light skin. Now you're not saying that everyone has blonde hair. You're just saying that if they do, they have light skin. You're implying a correlation in all instances where P of X is true. Now universals are very easy to disprove. If I say everyone has blonde hair, all you have to do is find someone who's got brown or red or black hair, and my statement is disproven. This is called a counterexample. One counterexample will destroy a universal statement. However, proving a universal is much more difficult. If we have a large domain, in order to definitively prove your universal, you'd have to hunt down everyone in your domain and see that your universal applies in every instance. Often domains can be infinite, or at least near infinite, so this is often impossible. What is done instead is that you try to disprove your universal statement. Every time you try to disprove your universal, and fail to, you have more evidence to support yourself. This is the case for most scientific theories, such as evolution. You could say, for all x, p of x means evolution applies to every x, where the domain is every cellular organism. In order to prove it, you'd have to hunt down every possible variety of life and see that evolution applies, which is, as previously stated, impossible. However, scientists constantly try to disprove their universal theories, and those which have failed to be disproven time and time again are accepted as true, though they have not been definitively proven. The other kind of quantifier is the existential, which uses a backwards e. Backwards ex means there is at least one x. So keeping p of x the evolution statement, there is one x p of x would mean there exists one x for which evolution applies. This is very easily proven. There are millions of organisms studied for which we know evolution has occurred, though we'd only need one instance for our existential statement to be true. As you probably can see, existential statements are not as useful as universals. You're saying, this applies in this one instance. Science tries to look for generalities, laws and equations that can be applied across the board in many areas. You typically never see formulae for extremely specific situations. The other thing about existentials is that you can never disprove them, given an infinite domain. I could provide lots of examples that don't follow if there is an x, p of x, but that doesn't matter, because the statement says it only has to apply to one thing. One thing in all of infinity, the proverbial needle in the haystack, where the needle looks like hay. Now let's say that p of x means x is God. Then, there is an x, p of x would mean there exists a God. Disbelievers often mistakenly say that there is no God cannot be proven because you can't prove negative. This is not true. What is true is that you can't disprove the statement there exists a God because it isn't existential. You can say, well, there's no God over here, or over here, or over here, all day long, but you will never disprove the statement because you have an infinite domain. Whereas all a religious person would have to do is offer up definitive proof, and the issue would be settled. Therein lies the main difference between universals and existentials. A universal is disproven by a single counterexample, but is difficult to prove. An existential is proven by a single example, but is difficult to disprove. But like all the failures to disprove evolution mount up as evidence for it, all the failures to prove that a God exists mount up as evidence against it. So while I may accept as truth that there is no God, I can only ever say that there is an enormous lack of proof for God. Because who knows, maybe some theologian will finally offer up conclusive proof. And that is logic.